Hello friend, we are going to discuss an interesting topic, nodal analysis by using Kirchhoff current law. Let's start our topic directly. First, going to the nodal analysis, we will discuss a little about the Kirchhoff's law. Kirchhoff's provide us two laws, the Kirchhoff voltage law, which is also known as the KVL. And another law which is Kirchhoff current law, which is also known as KCL. The both laws are the basic key for analyzing a circuit in a circuit analysis. Let's get a brief intro about KVL and KCL. According to KVL, the algebraic sum of all the voltages in a loop must be equal to 0. In a loop, we have a voltage rise and voltage drop. We take voltage rise as a positive and voltage drop as a negative, and the algebraic sum of all the voltages must come equal in a loop come equal to 0. In a Kirchhoff current law, the algebraic sum of all the current at a node must be equal to 0. We will discuss the KVL in our next video. Let's discuss the KCL in a little bit detail. Kirchhoff current law is also known as the law of conservation of charge because the charge is conserved on the node with no loss of current. That is, charge neither be created nor destroyed. So the charge enter in a node must be equal to the charge leaving a node. We can also say that the sum of the current entering the node must be equal to the sum of the current leaving a node. Let's take a node A. Let's assume current I1 enters from this branch and I2 enters from this branch, and I3 and leaves from this branch. So according to the KCL, the I3 must be equal to I1 plus I2. We have one branch from where current leaving and two branches from where current entering. The sum of the current entering the node must be equal to the sum of the current leaving the node. This is the basic idea of the Kirchhoff current law. Now coming back to the our main topic, nodal analysis. For analyzing a circuit through nodal analysis, we can use either KCL or KVL. In this video, we will solve this nodal analysis using KCL. Now coming to the procedure of the nodal analysis. First of all, identify the nodes of the circuit. Secondly, second step, take any node as a reference. For our calculation simplification, we take a node having more connection as a reference. So at the end, if we have n nodes in a circuit, we get n-1 nodal equations. After taking a node as a reference, give a variable name to other nodes. After assigning the variable names, we have to construct equations according to the KCL. After constructing equation, we solve that equation simultaneously and take out our required result. Now coming to an example and get a better understanding of the nodal analysis. Here we have three nodes: node 1, node 2, and this whole as node 3. We can take any node as a reference. Let's take node 3 as a reference. According to the third step, we have to name the other two nodes. We name this node as a v1 and this node as a v2. Now coming to the fourth step. In the fourth step, we have to find the equations of the node 1 and node 2. For node 1, we have to write the currents of each branch that is leaving or entering that node. The current leaving that node is taken as positive, and the current entering that node as a negative. The current here we have 2 ampere current entering that node 1. This will take as negative, and this current is leaving the node, so we take it as a positive. For this branch, resistor, we have to find the current using the Ohm law. The Ohm law says that I is equal to V by R. Now, constructing the equation of node 1. The current leaving over here, we take it as a 4 plus the current leaving from this node downward. This in this branch we have V1 by 2, and current in this branch we have the voltage across a resistor V1 minus V2 divided by 2, and current entering is minus 2 equal to 0. Now equation of the node 2. Here current entering the node 2, this is also the current entering the node 2, and here we take a current leaving the node 2, here we take leaving the node 2. Then the equation came as V2 by 8 plus V2 minus V1 by 2 minus 4 minus 7 equal to 0. Here I want to mention one thing. While taking node equations of the node 1, we take the voltage V1 is higher than V2, so that the current leaves out of that node. And for node 2, we take V2 as higher than V1, so that the current leaves the node 2. So in equation for calculating the current of same branch, in node 1 equation V1 minus V2 by 2, and in node 2 equations we take V2 minus V1 by 2. So now we have to simplify these equations. After simplifying the equation of the node 1, we get 2V1 minus V2 equal to minus 4, and for node 2 we get minus 4V1 plus 5V2 equal to 58. Now we have to find the values of V1 and V2 from these equations. There are different methods. One is where take out the V1 in term of V2 and put the value of V1 in equation 2 and solve for V2 answer. Another method is elimination method. In elimination method, we have to cancel a variable from an equation. From here we can easily analyze that if we have a 5v2 over here, then we can add these two, and we can add them and can cancel v2 from the whole term. So for that we multiply by equation 1 by 5 and then add that equation with equation 2. Like after multiplying equation 1 by 5 we get 10v1 minus 5v2 is equal to minus 20. Now adding equation 2 and 3 and equation 2 we get an answer 6. v1 is equal to 68. After simplifying we get v1 is equal to 34 by 3, and similarly putting this value in equation 1 we get v2 is equal to 80 by 3. So we find out the voltages of the node. Here we get 24 by 3 and here we get 80 by 3, and here we take it as a reference. Now after we getting the voltages at a node, we can easily find the current of each branch. Like across this resistor we have voltage 24 by 3 and 24 by 3 divided by 2 and 24 by 6, and we get an answer of the current in this branch. Similarly we can find a current in any branch. This is in nodal analysis using the KCL. In our next video we will solve the nodal analysis using KVL, and we will verify this example from with the nodal analysis using KVL. Thank you for watching my video. Stay tuned. We will be back soon, inshallah.